So welcome. So we're going to do this chapter on sources of magnetic field. We've learned something about magnetic fields, and now we're going to say, well, how do we generate magnetic fields? And of course, we're talking about using current carrying wires in order to do that. So let me set this to 55 minutes so I don't overrun. I set to 50 because I'm going to get a bit tired, so we'll do that. And what we're going to look at, a thing called Boyer-Savat's law. Then we'll look at force between parallel current carrying wires, and we'll go on to look at Ampere's law, which is important, and magnetic flux. And then we get into Gauss's law of magnetism and displacement current. Displacement current is a fiddle they do because of capacitors. And Gauss's law of magnetism has a bit of a trivial answer. The answer is 0. So we kind of like, we have some skills at the beginning, and then towards the end we have stuff that, although if you were going to become physics majors, then you'd go on, or if you become electrical engineers, you're going to continue with it. But as far as we're concerned, we kind of get to that point, and we just kind of look into the distance at that point. Boyer-Savat's law basically says, I'm not worried about charges moving through a magnetic field. So you've got to kind of like stop thinking about that visualization. That's what we did all last chapter. We talked about charges moving in magnetic fields, be they an independent charge like in the fine beam tube, or be they a charge flowing through a piece of wire. We did all that last time. Now there's no magnets anywhere. There's just current carrying wire. And that current carrying wire is now creating a magnetic field. So now we're just concerned about, well, what field could I create 5 meters away from that current carrying wire? Can I calculate that? And here's the issue. We're going to start off with a general case. So I can tell you conceptually that if I have a current carrying wire coming out of the screen, so I'm going to put a little dot there to tell me the current's coming out of the screen, I can tell you that there'll be concentric rings of magnetic field. The magnetic field would look like that. And that they'll have a certain direction to them. And the way you get the direction is you use your thumb in the direction of the current and your fingers point in the direction of the magnetic field. So the magnetic field will be in that direction. It will be circular. So never ending, no beginning, no end to speak of, and be like that. And if it was going into the board, again it would be concentric rings of magnetic field lines. And using the corkscrew rule, I can see now that that goes in that direction. And this is just caused by the current inside the magnetic field. Sorry, this is just caused by the current in the wire. So conceptually, not bad.
Sir, a question.
Yeah.
So I take it that whenever the flow of current is heading in the direction of the observer, it's always heading in a counterclockwise movement?
If you look at it coming towards you, you're seeing a counterclockwise magnetic field lines. Yeah. Okay. So that's the name of the game. I'd like to know how strong the magnetic field is there. That's my point of interest there. I'd like to know how strong the magnetic field is there. And that's the game I'm going to play. I want to know at that point, what is B? Just like we did with Gauss's law. We said at that point, what is E? So we're playing that same game again. We're going to go to the general case. And here we have a point of interest. And it's some distance away from a generic piece of wire. It's not a straight piece of wire. It's a curvy piece of wire. And what we're going to do is we're going to divide this up into a series of sections. And we're going to say, well, let's just, figure it out for each section and then add it together. Well, all right, so we have a ds. That's our little bit of length. and we have a r hat. That's a unit vector pointing from our little wire bit of interest in the direction of the point of interest. There's an angle between those two. There's a distance between the point of interest and our little wire segment. We say consider the magnetic field little b, the dB, the little bit at a point P caused by the current flowing through a length element ds. So just in that little length element, that ds, what's the little bit of magnetism caused there? The position vector relating to the length element to ds and the point is r. So you could have an r vector going from there to there. This is the magnitude of r, and this is the unit vector r. What we say is the little bit of magnetism, little bit of magnetic field, is a constant. It's mu naught times divided by 4 pi times the current times a cross product ds crossed with r, and that is r hat. I'm sorry, in the notes I put down r with the little vector on top of it, and that is r hat divided by inverse square. That's also r hat down there. Okay. Where mu naught is the permeability of free space, and it's got units of, it's 4 pi times 10 to the minus 7 Tesla meter over amps. That's from one little element. What about all these other little elements? Well, we just add them all together. We integrate them. Okay. Mu naught's a constant. And for a given piece of wire, I's constant, because whatever goes into one element goes into the next element. And 4's a constant, and pi's a constant, so they can all come out. And so we have the integral of all the little ds's crossed with r hats over r squared. The r's are not a constant, are they? They're different distances. Yeah? So they can't come out. And we have this cross product, which is the magnitude of ds times the magnitude of r times the sine of the angle between, and the angles are changing, you know, depending upon where we are. So we can't take those out. So we end up with this general form, and this is Boyer-Servat's law, and I'd like you to know that law. So just commit it to memory. I can assure you there's going to be a question on the test using this law. So you're going to need to know it, but also for a quiz next time, Boyer-Servat's law. You don't need to know the first form, know the second form. So B is equal to mu naught I over 4 pi integral ds crossed with r hat over r squared. Now that looks horrendous, but the fact is we're going to use symmetry. So I'm not going to ask you about potato-shaped pieces of wire around an arbitrary, you know, point. I'm going to give you very specific geometries. And the geometry I like most is the circle. Because if I say the point of interest is in the middle of a circle, then the first thing you know is that the R value is the same for every piece of wire, every section of the wire. And the second thing you know is that my unit vector R hat and my ds are always at 90 degrees to each other. So all the difficult stuff of that integration goes away because we pick the symmetrical solution. So here's a typical example. I'm sorry, before I started videotaping these things, I noticed that people were sometimes coming to my office and they'd have notes that were incorrect. And so the question was it me that had written it wrong, or was it them that had copied it wrong? And on questions like this, you're flying through it. So what I decided to do was maybe I could just write it out longhand, and then at least I know they have the full answer, and they don't need to worry so much about having the putting all the notes down. So maybe that's a solution. So I got, on this chapter, I got pretty well, the answers are already there. So, and is this the version of notes that you're seeing in your notes?
Yes, sir.
Good, okay. So what we say is that a current carrying wire bent in a complete circle, that's the thing I'm going to change. Maybe I'd give you a half a circle, Maybe I'd give you a quarter of a circle, maybe 7/16 of a circle. You know, this is a complete circle. It's all of a circle. Use the Boyosat method as taught in class to show that B at the center of the circle, so B at this point here, is equal to mu naught I over 2R, where I is the current flowing through the wire and R is the radius of the circle. I'm not going to ask you that in a test. I would say, what is the, rather than show that it is. Here's my diagram. The only thing I don't like about this diagram now is that I wish I'd done my R hat that way, but, you know, hey, whatever. So, B is equal to mu naught I over 4 pi integral of ds crossed with R hat over R squared. R is constant. That's the first thing to recognize. R is constant for all ds's. For all ds's. It's constant for all these little ds's. Okay, that's good. So I can take it out of the integral now. So I have mu naught I over 4 pi R squared. Then I have this integral ds crossed with R hat. And the second thing I realize is that ds is perpendicular to R hat. So in the expression ds R hat sine 90, sine 90 is 1. So let's just ds cross with R hat goes to ds R hat sine 90. Sine 90 is 1. R hat is 1. So this comes down to ds. It's the integral of that, is the integral of that, integral of that, and that equals the circumference. Yeah? All those little bits of ds's, you add them together, you get the circumference. So I say ds is perpendicular to R hat, and R hat is equal to 1 because it's a unit vector. It's a unit vector. You get this little hat on top. It's a unit vector. It's got a magnitude of 1. So I have mu naught I over 4 pi R squared times the integral of ds. Well, the integral of ds is the circumference, 2 pi R. So 2 goes with that 4. Pi goes with that pi, one of those r's goes with that, so I end up with mu naught I over 2r. Well, r is actually a value of big R in this case, so B is equal to mu naught I over 2r. Cool? Yep. And what did I forget on there? Teslas! Shame on me. So, I don't know what you feel about problems that only involve letters. I had a theoretician buddy at USF who would teach general physics and would never give them a single number, basically. And he'd say, well, I mean, it's easier not to have to deal with numbers. Numbers are confusing. And I could never tell whether he was kind of like a bit ingenuous, or whether he really did get that for most people, numbers are like the life raft, you know. You shove numbers in and you kind of know what you're doing. And letters are a little bit stressful. I was just teaching one of the Physics 1 things which has a derivation like this. And some of the people in class were saying, why can't we put numbers in? I was going, you can put numbers in. When I was a student, I would have put numbers in relatively quickly. But here's my plea to you about not putting numbers in early, and that is the fact that if you put 2 numbers in, you know, R equals 4 and V equals 8, and they're multiplying, so then you get 32. As soon as you multiply them, you lose where they came from in your mind's eye. And so when you're trying to check your answer, you've got to do all that math to check your work. Because you've got to say, what did that 32 come from? Whereas if you leave it as R and V, you can say, oh yeah, they multiply together. It doesn't matter. So to check your work, it's actually easier if you leave the letters in longer. And sometimes a letter will completely cancel out because it's on top and bottom of, say, a function, and you don't need to worry about it. And then thirdly, it enables you to do this, which is you end up with a generic equation for something. You know, every time you have a circle, if you want to know the magnetic field in the middle, it's mu naught I over 2r. You developed an equation. Now, I understand perfectly when you first begin, that's not the kind of thing you want to be messing with, but I want to encourage you that there is value in getting more used to not putting numbers in. And I'll tell you now, there's a certain cachet in answering questions that don't have numbers in. More in the physics side than the engineering side. So if you ask a question where there's no numbers anywhere, people go, whoa, look at that question. That's a very analytical question. It's not really harder than with numbers, it's uncomfortable. So I would encourage you to kind of like leave your letters in a bit longer and recognize there is a reward for it in the long run. But for a test, get the right answer. You need to show me the equation. You need to show me a diagram, show me what you're talking about. You need to show me the equation. You need to justify r is constant, ds perpendicular to r hat, and r hat equals 1. Show me these steps, okay? Let's do another one. A current carrying wire is bent in a semicircle. Oh, okay. I get it. You do the easy one, we do the hard ones. Okay, it's bent into a semicircle. Use Biot-Savat's law as taught in class to determine the value of B at the center. So there we are. I want to know my B here. Assume the current flowing through it is 5 amps. So let's do 5 amps. And that the radius is 2 meters. So this radius is 2 meters. Okay. I'm going to say, oh, okay, B is equal to, what was it? Mu naught over 4 pi. Mu naught I, wasn't it? The integral ds crossed with r hat over r squared. So that's not so bad. It's just an equation. Let's have a look. R is constant. Now, it's not down here. I'm saying it from here. That R is the same as that R is the same. For all these little DS's, R is constant, yeah? For all DS's. So we have B is equal to mu naught I over 4 pi r squared times the integral ds crossed with r hat. Okay. Oh! I know that ds is perpendicular to r hat, and r hat by definition equals 1. So B is equal to mu naught I over 4 pi r squared times the integral of ds, which equals mu naught I over 4 pi r squared, and the integral of ds is circ over 2, because it's a semicircle. Let's just say, let's be a bit cuter than that. Let's be a bit more generic. So it's a semicircle, yeah. 1/2 the circumference, yeah. Which equals mu naught I over 4 pi r squared times 1/2 of 2 pi r. Agreed? Which equals, those 2's cancel, mu naught I over 4, my pi's cancel, one of my r's goes away, those 2's cancel, so it's that. So B is equal to, leave the mu naught alone, I is 5 over 4 times r we said was 2, which equals 5 over 8 mu naught Tesla. You could leave the answer. Actually, what I'd probably want you to do is work it out. So I'd go 0.5 8s are 40, 6 8s are 48, carry 2, 2, 5, mu naught Tesla. I'm just getting to the stage where what I noticed was, I'd say to people, just leave it as a fraction, and people in other questions would have square roots left in there. And I'd say, well, you got to work out the square roots, and they go, but you said we could leave it as, you know, well, a fraction not including the square root. And then I'd find that some people would make a mistake on that last bit, and the part of me says, man, you know, you got to check your work. So I felt like I needed to ding them a little bit because they made a mistake on that last bit, and other people wouldn't show that last bit. So it's like, man, what do I do now? You know, do I not ding this person because this person didn't even bother writing it down? It's like, you know. So now I'm saying, get me, unless otherwise instructed, get me a decimal answer. But I'm going to tell you to leave the mu naught in. For homeworks, you know, work it out. But otherwise, for the test, just leave it. You know.
Question.
Yeah.
The integral of ds. If we didn't jump to the like if it wasn't intuitive that it was going to be 1/2 2 pi r. If we wanted to do that integral, what would it be? It should be some variable, right? But is it little r? Is it what exactly? I would think you would take the integral from 0 to pi.
I guess so, yeah.
But what is that integral? Is it? Then how would you relate?
You'd have to have a function for that circle, so it would be the function of the circle. I have no idea how I'd do that. It would be the function of a circle integrated between 0. It would be, I don't know. You try to do math. Turn that off. I've never done it that way. So there's your homework problem.
Okay.
Sort it out.
Thank you.
Then tell me. It's like, but recognize it's, you know,
Of course.
it's a set piece. But yeah, you're right. You'd need some kind of function, and you're going to integrate between the limits. So it'd be the equation for a circle, I guess.
I was just curious because I know on the test you've already said that you're going to give us a circle, whether it's just a bit of it, but I would actually be curious as
Yeah.
to how to do that potato-shaped wire.
Yes, yeah, and that's beyond where I go.
Okay.
It's like, I'm not sure I could ever do it, but, you know, I've certainly not done it in 20 years. So maybe 40 years, actually. So just by the by, I had one of my students, I'm sorry. So one of my students, I'm trying to turn it off and it's not going off. So one of my students was like that and would basically say, I'd find it all over the board. He would work things out from first principles. And, you know, power to him, you know. It ate some time up for him, but he wanted to be rock solid on, you know, he wanted to practice his math as much as anything, you know. And it served him well. You don't need to do that though, but it served him well, you know. It's not, and it's not that, so, and just so you don't go the other way, it's not that I'm the only person in the world who relies on the symmetries. That's the physics kind of like, you know, snigger, you know, let the mathematicians work at it, but we're smart enough to look for the symmetries. So there's a tradition of only asking partitions of a circle. Supposing I had told you that it was a quarter of a circle, can you see how you'd write a quarter in there rather than a half? If I told you it was 15/16 of a circle, you'd write 15/16 in there. Yeah? So don't be thrown off by that. The other thing I can do, though, to make it a bit more interesting is not give you the radius, but give you the length of wire. And say this length of wire is a half of a circle. And so then, probably the most straightforward way is you'd say L is equal to 1/2 of 2 pi r. So you'd say r is equal to L over pi. And that would be a number over pi, and you'd work that thing. The temptation is you say, well, that equals L. And it does. But then you've got to figure out what that is down there. So I think the easiest way is, if I give you the length, just work out what the radius is and then do the problem. You know. Cool. This is reminiscent of a problem that we did in electrostatics when we had the charge on a ring. And we said, we don't want the electric field, we don't want the voltage at the middle of the ring, we want the voltage along the axis. And in that case, the voltage is a scalar. So it was actually pretty straightforward. It was just, oh, well, we just basically got to work out this hypotenuse distance. This is a little bit more involved. And the reason why I want you to see it is because I just don't want you to be cornered by, again, letters. There's a whole bunch of letters thrown at you. And there's these powers, 3/2. You know, oh, I remember when I see that, I go, oh, man, where did that come from? Well, it comes from Pythagoras, you know. When you get r squared plus x squared to either the half or 3/2 or something, you're playing with Pythagoras. It's like, now with experience, and now it's not on a test for me, I can with a cool head say, yeah, it's going to be Pythagoras is going to be involved. But I remember at the time getting stuff like that and going, I have no idea. You know, I have no idea. It's like, I couldn't believe where that came from. So I want to show you it just so that you don't get so cornered by it. So a current carrying wire is bent into a complete circle. Use Boyer-Savat method as taught in class to show that the magnitude of the x component. So I'm doing that red arrow. The magnitude of the x component at B, of B at a point on the axis of the loop is given by that. Okay. So let's start off by writing down Boyer-Savat's law. So we're going to say B is equal to mu naught over 4 pi times I times the integral of ds. Sorry, which way round is it? Is it ds cross ri? It is, isn't it? Yeah, just a momentary. Yes. ds cross r. Remember, for these guys it counts, doesn't it? You can't just like finagle it round. R squared, okay? Okay, so here's my little ds, and there's an angle here, and that's the same as the angle there, etc., etc., etc. Let's do this first bit and just figure out what the B is, not worry so much about its direction. So can you see how, if I have a cone of current, if I have a ring of current, then I'm gonna for each little ds, I can imagine the little radius vector pointing like that at the same point, yeah? And can you see how each one of them is going to create a magnetic field that's going to be pointing, it's hard to draw, but it's a magnetic field that's pointing at 90 degrees to it. So I get a cone of magnetic field vectors, and I'm showing one of them here. And these are going to combine to give me one final magnetic field that is coming out in that direction, yeah. And the reason why I don't get a vertical component is because that one up there is cancelled by one down there, the components. But the x's add, but the vertical ones cancel each other out. Okay, so, all right. So let's just follow our nose and see what we get. So we say, well, okay, this is mu naught over 4 pi times I. And what can we say about this? I can say my R is constant. So again, that's going to be R squared, the integral, ds crossed with R hat. So I just took my R squared out, because on this, all these R lines are going to be constant. And then I need to think about my ds. Oh, I'm sorry. I've got to be a little bit careful here. My R is not that R there. My R is that line down there. Agreed? So, yeah, R is not equal to R. We've got to be clear about that. And then what about ds being perpendicular? Well, ds is still perpendicular to R hat. It's just they're not in the plane of the circle, but they are still perpendicular. Agreed? So I can say ds is perpendicular to R hat, and R hat is equal to 1, just like we had before. So then I say, well, B is equal to mu naught over 4 pi R squared, the integral ds. This is like the same old, which equals mu naught over 4 pi R squared times, and it's a complete circle, so it's the circumference, which equals mu naught over 4 pi R squared times 2 pi. Now I got to be careful, because this is not 2 pi little r, this is 2 pi big R. Yeah, got to be careful, because now that R on the bottom, which is the distance from the little bit of length to my point of interest, there's my R, there's my little r, and that there is my big R, and they're not the same. So when I'm talking about my circumference, I need to think in terms of the big R. But when I'm talking about my distance from the ds to the point of interest, I'm talking about my little r. Unfortunately, the letters are kind of like, the big R is a shorter distance than the little r is. Can you see that though? So that's my circumference R, and this is my separation R. And so in here, I can't cancel these guys like I could do before. Yep. But it's up to there, it's the same. Up to there, it's just like the same old, same old. It's the same old, same old. But now we start saying, okay, well, then I have mu naught over 4 pi. Let's express this R, this little r, which is that guy, in, oh, well, that's going to be the square root of r squared plus x squared. Agreed? Using Pythagoras. But of course we have to square that because it's r squared times 2 pi r, which equals mu naught over 4 pi, and that's going to be simply r squared plus x squared, because I'm squaring the square root. That I'm squaring the square root. And this is going to be times 2 pi r. And then my mu naught stays in. Did I drop my I somewhere? Pretty early on, I seem to have dropped my I. So then I have mu naught I, and that, let's turn my color pen. So that color pen, let's do that again. Let's go to red. So that is going to go with that and leave me 2, and that guy is going to go with that. So mu naught I times R over, and I have a 2, and I have a r squared plus x squared. Now, what is that? That is this magnetic field, and the magnetic field, remember how we do the corkscrew rule? We have our current and we have our, yeah? So that piece of ds is making a magnetic field which goes in a circle, and there's the component of it. That is that. We just worked out what the arrow was. Yeah? In the previous bit, that was going into the page. The arrow was going into the page. That little point there, if I looked at that piece of wire there on end, the field lines would be going round. And so at this point B, that would go into the page. Here, I've got my currents coming towards me, and I'm doing the things, and that's going up like that. It's good. Okay? So that's one of them. I got a cone of them. I've got a whole, and every one of them is going to be like that. So I can take one of them and I can say, well, let's divide that up into its vertical component, its horizontal component. And can you see how all the vertical components will cancel because they're going to be opposite each other? For every one up, there's one down. For every one to the right, there's one to the left. For every one at 3 o'clock, there's one at 9 o'clock. For every one at 4:30, there's one at 10:30. For everyone at 1:30, there's one at 7:30. You know, yeah, they're going to symmetrically going to cancel. But these ones that are sticking out are going to add. Yeah, they're all going to be added, and so I got to work out the component of this. So what I do is I say I have mu naught I r over 2 r squared plus x squared, and then I got to say, well, hold on, I want the component of that, which would be cosine this at angle, and that at angle is the same as that angle there. Big angle, little angle, big angle, little angle, big angle. And that at angle, or if you like, now I want it in terms of r and x, tan that angle is equal to opposite, which is x over r, and cosine that at angle is equal to the cosine of that would be r over the square root of r squared plus x squared. That's my r squared plus x squared square root. and there's my r. So that angle is the cosine of r squared plus x squared square root over r. So that means that this now equals mu naught over times I times r over 2 r squared plus x squared times r, the square root of r squared plus x squared. So this is equal to mu naught I r squared over 2 and r squared plus x squared, and it's not to the half and it's not to the 1, it's to 1.5, which is 3 over 2. So there we have it. So it's a journey, you know. But if you think about it, it's basically same old, same old. So this is an example where I can't see the end of that problem when I started. I don't remember all this. I haven't done this in at least a semester, so I don't remember this. But I do know that. So it's to do with Boyer-Savat, so I'm going to start down Boyer-Savat's. And then I'm looking, I'm saying, well, yeah, I can still take my r out, so I can simplify it by that. And then, yeah, I can still say these guys, so these are my old tools, I'm finding, well, yeah, it's still the integral of ds. And I'm looking, I'm saying, well, the ds is now my circle, and then the alarm bell goes off, and I go, well, hold on. There's my r, and there's my r for my circle, so these two r's are not the same. And I think that comes because of the diagram. I'm visualizing there. Mathematically it's correct, but I don't think necessarily you get it from the math. You really get it from the visualization. They're two different things. Okay, so I'm kind of on my way. And then I say, well, okay, that r is that, but that little r, there's none of that little r in my answer, so I've got to get rid of it. So, it's Pythagoras. So now I use Pythagoras on that. And then I bring it and I simplify it. I'm still not got the right answer. And I'm going, well, my work's okay up to now. Then I go, oh yeah, but it wants the x component, so I've got to break this up into components. So whereas I didn't bother drawing the vector when I'm just looking at the end of the thing, now I'm off axis, now I'm further along the axis, my component matters. And so then I've got to do, it's an angular thing, etc., etc. And I'm saying, how can I define that angle? I need the cosine of that angle, and that angle is linked to r and x, like that. So, and you just work through it. The first time you do it, you kind of go, whoosh. But once you've seen that, and you've seen, you know, you build faith, and you kind of know your direction, then they get easier, you know. They just get easier. I wouldn't ask you a question like that on the test, but I'd like you to see it, you know. Okay. Force between, but let's go back. But one of those for sure. 1/16 of a circle, quarter of a circle, something like that. That's fair game. You will get a Boyer-Savat's question. Okay. Magnetic force between two parallel currents. So one wire causes a magnetic field that the other wire travels through. So the charge carriers in one wire get affected by the field caused by the other wire. And it doesn't matter which way around you do it. And what you find is you can't talk about the force, because the longer the wires, the longer the current flow, the more the force. So we talk about the force per unit length, and here on the word processor you can see that L is different from that I, but I can't see it so well today. So to my mind, you know, do that, so make it stand out. The force per unit length is mu naught I1 I2 over 2 pi A. Yeah, it's going to depend on the current through the first wire, because that's going to give you a stronger field if that's stronger. And it's going to depend upon the current in the second wire, because if you get more current, you get more charge carriers flowing, so you get a bigger force. And the rest is like, you know, well, all right, I would expect the separation. If the separation gets bigger, then the effect should get smaller. So it kind of makes sense. I kind of justify whether it's a over 2 pi, over 2 pi a or over 2 pi a squared. I can't really justify why it's not an inverse square relationship. Well, there's a certain cylindrical symmetry to it, but that's kind of hand waving, you know. But know that equation: when both wires carry current in the same direction, the force is attractive. I don't have to remember that. Here's a wire coming towards me, and here's a wire coming towards me, with the current coming towards me. I look at the one on the right, and I say, oh, my magnetic field goes like that. Yep. Corkscrew rule. Yep. I'm going to change colored pen so you can see this a bit easier. So now, man, I keep missing that today. So now for this wire on the left, my charge carriers are moving towards me. So the V is towards me and the B is downwards. So my force is in that direction. You see that? The B, I can't reach up there, can I? The V is towards me, and the B is downwards. So that means because QV cross B, the V is towards me, the B is downwards, so the force is that way, pointing towards the other wire. So I don't have to remember that similar directions of currents leads to attraction. I can figure that out anytime I need to do it. Yes?
Forgive me, sir, but you said the two wires are attracted towards each other?
The
The direction of current is the same, is it not?
yes.
So shouldn't the magnetic field between the two of them be in the same direction as well?
If I have that guy, then the magnetic field is that way for that one. And if I have that guy, then the magnetic field will be that way for that one.
Okay, opposite. I see.
Okay, so when the current flows in opposite directions, the force is repulsive. You can remember those, or you can be able to figure them out. You know, this system is used to define the amp. Here's a little bit of an aside. So there's a thing called the National Institutes of Science and Technology. It's in Gaithersburg, Maryland, and they earn their money by basically measuring fundamental constants. And I think I've told you this. So when you go to Publix and you get, you know, a pound of meat, they actually that scale, that electronic scale, has to be calibrated on a regular basis. And I don't know about the States. I believe it's the same, but in Britain they have an organization called the Weights and Measures. And each shop will be visited by one of their inspectors on a reasonably regular basis. And they will check that the scales are all correct. Because if I just turn my little calibration knob, I can make a lot more profit. If my pound is really 3/4 of a pound, I just charged you 50% extra, basically. You know, or 30% extra. I just took money away from you. So they stopped that. So they have weights and measures. Somebody's got to have the machine that checks it. That machine needs to be calibrated, and somebody has to have a calibration for that. So you get secondary and tertiary standards going throughout the nation and across the world. The meter, when we buy our meter rulers, we're buying them from a manufacturer who marks on a piece of wood the position for the different divisions. They have a machine that does that. Who calibrates that machine? There's a standard that they'll buy, and that standard was made by somebody who makes standards. And how do they calibrate it? They buy a standard, and so on and so on. It goes back to NIST. It actually goes, in that case, it goes back to, originally it went back to France, because they had the meter in a cabinet, you know. Well, that's a bit of a pain. If you've got to go back to France for the kilogram, you've got to go back to France for a meter. You know, You want to be able to do things somewhat independently. And so they started doing different ways of getting to the same thing. And one of the ways of getting, for instance, one of the ways for getting to the meter for now is it's been defined in terms of a certain number of wavelengths of a specific color of light. You don't need that meter in France. You can, light is light. You can just, now you can argue about how do you measure, how do you know you got the right frequency and all that kind of stuff. But, So they're like these secondary standards, and one of the things they've done is, we say that an amp is a coulomb per second. Try measuring that. That's a total pain. That's chemistry. Counting the charges until you get to a coulomb, that's not a trivial thing. So somebody came up with a better standard, which is you get two wires that are 1 meter apart, and you have 1 amp flowing through them when the force is 2 times 10 to the minus 7. That's going to be newtons per meter. So when you have those two, you got an amp flowing down the wires. So it's kind of interesting. Consider 2 parallel wires. One wire carries a current of 5 amps to the right. And the second wire carries a current of 4 amps to the left. And the distance between them is 2 meters. Are the wires attracted towards each other or repelled? What did we say? If it's that, the forces are attractive. If it's that, the forces are attractive. If it's that, the forces are repulsive. And you can figure that out if need be, yeah? If I wanted to, I'd go like that. I'd go like that. I'd say, okay, my magnetic field is in that direction caused by this guy on the right. My charge carriers are coming out, so my V is out and my B is up. So my force is in that direction. Can you see that? So corkscrew rule, the corkscrew rule on the X tells you that the magnetic field going through the left-hand wire is upwards. I know my current in that left-hand wire is coming towards me, so that's a V. So you point your fingers towards the V, then you rotate your hand until you can rotate your fingers towards the B, because it's V cross B. Wherever your thumb points, that's going to be your force. So then I can say that this is going to be that which is repelled. And then, what is the magnitude? I say F over L, magnitude per length. I say F over L is equal to mu naught I1, I2 over 2 pi A, a bit like 2 pi R, a bit like a circumference really. So mu naught 4 times 5 over 2 pi times 2, which is 20 mu naught over 4 pi. And so F over L would equal, just leave it as 5 mu naught over pi, and that's going to be in newtons per meter. Cool. And let's stop there. Let's take a break, and we'll do Ampere's law.